Hello class, everybody stand for the prayer. Miss Arensha, can you lead the prayer? Okay. Amen. Mathematics is engaging. Students here are all amazing. Let us do a magical learning, but before that, let me greet you a good morning. Good morning, class. Okay, class, before you take your seat, kindly pick up those letters around you and please arrange your chair in a straight line. Okay, very well. You may now take your seat. Okay, let us check your attendance. Miss Alvarez, who is absent for today? None? Okay, very good. Okay, class, let me introduce myself. I am Ma'am Anime Fornal, your math teacher. In my class, I have 3 rules that everyone need to follow. First, when I am talking, please listen carefully. Second, if you want to answer, just raise your hand. And third, respect me as your teacher. Is that clear, everyone? Okay, for today, I prepared a short game for everyone. I will show incomplete word, and after that, if you have an idea what is the missing letter, and if you know the correct answer, please raise your hand. Is that clear? Okay, let's start the game. Just raise your hand if you know the answer, and I will give plus points for those students who can give a correct answer. Is that clear? Okay. For number 1, what do you think is the answer? Yes, Miss Achilles. Correct. The correct answer is calculus. And the missing letter is A, U, L, and U. Number 2. Yes, Miss Achilles. Correct. The answer is differentiation. The missing letter is F, F, R, N, A, O, and N. Next, let's proceed to number 3. Yes, Miss Bitong? Correct. The answer is integration, and the missing letter is N, T, G, and T. Next, let's proceed to the last number. Yes, Miss Valenzuela? That's correct. The answer is derivative, and the missing letter is E, L, A, and V. Congratulations to those students who got a correct answer. Okay, students, our topic for today is all about Gottfried Leibniz, the calculus controversy. We have here a learning objectives. Can you please read, Miss Alvarez? Okay, thank you. Do you know who is Gottfried Leibniz? Gottfried Wilhelm von Leibniz, a German mathematician and a philosopher. He was born on July 1, 1646 in Leipzig, Germany. At age of 15, he enrolled at the University of Leipzig, where his father used to teach and earned both a bachelor's and master's degree in philosophy. He received his Doctor of Law from the University of Altdorf. Gottfried Leibniz discovered infinitesimal calculus, a distinction he shared with Sir Isaac Newton. However, each one made this discovery alone, not while working together. Infinitesimal calculus is a branch of mathematics that is concerned with differentiation, integration, and limits of function. Leibniz also developed the law of continuity and the transcendental law of homogeneity, cutting edges of theories that are published or used in mathematics until mid-20th century. Between his work on philosophy and logic as his day job as a politician and representative of the royal house of Hanover, Leibniz still found time to work on mathematics. He has perhaps the first to explicitly employ the mathematical notion of a function to denote geometric concepts derived from a curve, and he developed a system of infinitesimal calculus independently of his contemporary Sir Isaac Newton. He also revived the ancient method of solving equations using matrices, invented the practical calculating and the machine, and pioneered the use of the binary system. Gottfried Leibniz was the first person to provide a description of a pinwheel calculator and invented a device of his own. Okay class, look at the picture. What do you think is this? Okay, this is Leibniz pinwheel calculator, also called step reckoner. It was built in 1673. The step reckoner expanded on Pascal's ideas and did multiplication by repeated addition and shifting. The Leibniz wheel consisted of a cylinder with a set of teeth of increasing length. It was used in automatic mechanical calculators until the development of the electronic calculator in the mid-1970s. Like Newton, Leibniz was member of the Royal Society in London and was almost certainly aware of Newton's work on calculus. During the 1670s, slightly later than Newton's early work, Leibniz developed a very similar theory of calculus, apparently completely independently. Within a short period, about 2 months, he had developed a complete theory of differential calculus and integral calculus. Okay class, look at the difference between differentiation and integration of Newton's and Leibniz. So let's focus first on differentiation. Newton used a dot over the dependent variable to indicate a derivative, two dots for second derivative, and etc. But Leibniz just used the dx and dy to indicate the infinitesimal increments in the independent and dependent variables. The use of the prime mark for derivatives dates from Joseph Louis Lagrange works in differential calculus in the late 18th early and 19th early. And now let's proceed to the integration. Newton never used one consistent notation for integration, sometimes using a bar above a variable and sometimes putting the variable in the box. We have come to use the Leibniz notation, which uses an extended s to indicate the sum of infinitely many infinitesimal quantities f of x for each infinitesimal increments dx between the two stated limits a and b. Unlike Newton, however, Leibniz was more than happy to publish his work, and so Europe first heard about calculus from Leibniz in 1684, and not from Newton, who published nothing on the subject until 1693. When the Royal Society was asked to adjudicate between the rival claims of the two men over the development of the theory of calculus, they have credit for the first discovery, and it is Newton, and credit for the first publication to Leibniz. However, the Royal Society, by then under the rather biased presidency of Newton himself, later also accused Leibniz of plagiarism, a slur from which Leibniz never really recovered. It's so sad. In addition to calculus, Leibniz rediscovered a method of arranging linear equation into an array, now called a matrix, which could then be manipulated to find a solution. A similar method had been pioneered by Chinese mathematician almost 2 millennia earlier, but had a long fallen into disuse. Leibniz paved the way for later work on matrices and linear algebra by Carl Friedrich Gauss. He also introduced notions of self-similarity and the principle of continuity, which foreshadowed an area of mathematics which would come to be called topology. Okay class, let's proceed to the binary number system. What is binary number system? Do you have any idea what is it? Okay class, binary number system, a method of representing number that has 2 as its base and use only the digits of 0 and 1. Look at this picture. This is an example of binary number system. Okay, class, I will give an example about binary to decimal. So, I have here an example. Look at this picture. Example, those at the top, which is the number 1, that is what we call binary number. And at the bottom of 1, or binary number, is what we call the base. The base with a power of 0, 1, 2, 3, up to 7. And now let's see how to get the decimal number. Let us start from the base 2 power of 0. Let us start from the base 2 power of 0. What is the answer? 2 raised to 0? Yes, that is 1. Now let's proceed to 2 raised to 1. And then, after you find the answer of the base 2 with power of 0 to 7, look at the binary number. Because you will multiply the answer of those base 2 with power of 0 to 7, and after that you will add all it. And the answer is 255. It was easy to solve, right? Okay. So ma'am, why 255 is the answer? Okay, let me explain step by step. Our binary number is 1. All of it is 1. After you got the answer in the 2 raised to 0, 2 raised to 1, 2 raised to 3, until to 7, after that, look at the binary number. You will multiply the answer into the binary number. And after you multiply that, you will add all the final answer. That's why the answer is 255. Okay, let me give you an example again. Okay, class, who can give the correct answer? Yes, Miss Achilles. That's correct. The answer is 149. Why? Because we have a binary number which is the 0, which is the 1, 0, 0, 1, 0, 1, 0, and 1. Why we have a 0? Start first to 2 raised to 0. So 2 raised to 0 is 1. 2 raised to 2 is 4. 2 raised to 1 is 2. 2 raised to 3 is 8. Okay class, after you solve all the base 2 with power of 0 to 7, you will add all it again. But after that, multiply it first into the binary number. Since we have a 0, like for example, in 2 raised to 1, the answer is 2. And then 2 multiplied by the binary number, which is 0. So 2 times 0 is equal to 0. And the answer is 0. And the final answer is 0. And after that, you will add all the final answer. And the answer is 149. During the 1670s, Leibniz worked on the invention of a practical calculating machine which used the binary system and was capable of multiplying, dividing, and even extracting roots, a great improvement of Pascal's rudimentary adding machine and a true forerunner of the computer. He is usually credited with the early development of the binary number system, base 2, counting, using only the digits 0 and 1. Although he himself was aware of similar ideas dating back to the I Ching of ancient China, because of the ability of the binary to be represented by the two phases on and off. It would later become the foundation of virtually all modern computer, and Leibniz documentation was essential in the development process. And that is the end of our discussion for today. Do you have any question? Okay, if there is none, Miss Orfiano, can you summarize the lesson and share what you have learned from the discussion? Very good. Thank you so much. Okay, class, prepare yourself because we have an activity and quiz for today. Thank you for your cooperation. Goodbye, class.